While we're here, I did promise you guys a take-home exam. We should look at when that's going to be issued. When did I have your homework due? The 8th, the 7th? The 6th? Next Wednesday. All right, so then I'll have the exam out. You guys can't see this. So you'll have the exam for the whole exam period. So we'll have it due. It'll come out next Thursday, and then it'll be out till Wednesday, May 3rd. Okay. Be just like last semester. Some of you know your last semester. It's cumulative, but not really. Half of it will be ciphered quality multiple choice, meaning that they're not really multiple choice questions. They do have four answers, and then a short answer kind of computational question at the end. Multi-part, straightforward. Be about half the length of a usual homework. And then the only rule, as you guys know, is Kayla and Allison are off limits. And I technically write that you guys can't collaborate, but I can't enforce that. So I just look at the exams afterwards and see the correlations, and that's about it. So it's not a big deal. Just a final little goodbye. So with atoms, we're not really done with atoms. We always have atoms in our lives. It's just that generally atoms combine to make molecules. So we should start thinking when we close up to kind of finish up chemistry, right? That was kind of always my goal, was to build chemistry from the ground up, and we haven't really gotten to actual chemistry reactions and stuff. But in reality, when you talk about physical chemistry in a traditional curriculum, we really only get to about where we are in 2 semesters. Physical chemistry is a rabbit hole, like many fields, and it's just hard to accumulate as much information about and sometimes doing all of Gen Chem, but at a high level. It's just not possible with the amount of different ways that we have to think about things. It's really a long-term process. So the whole point of PChem 1 and 2 is to get you thinking a little bit like a PChem. It's just kind of looking at chemistry from a different perspective. It's not about completing chemistry and having a complete picture, but rather to get you started on that approach if you're interested, or scare you away, whatever you prefer. Some people are interested. And it doesn't always have to click. Sometimes for me, it didn't click until I was in grad school, where I really started to realize that the way that we talk about chemistry in undergrad classes is always the way that chemistry works in real life. Physical chemistry was that language that we use to understand more technical and more complex things, and you don't really get to see it until you have to use it. I think this is probably the most useful couple of lectures that we're going to have. I don't know if you're supposed to get. Can you turn off the front light, Amelia? I'm sorry. Yeah. I don't want to say none of it's useful, but this is the thing that we can touch and feel the most, I think. And this is going to get us closest to organic chemistry that we'll feel. It's about building molecules from our orbital perspective. We have atoms with orbitals and electrons. How do we combine those atoms and orbitals together to make what we call molecular orbitals, right? And that's going to be our general approach. Is we're going to, again, do that bootstrapping process where we start with a simple problem, work our way up by using as the framework for our solution for the complicated problem an expansion on our simple answer, right? We treat complex atoms like smushed hydrogens. We treat harmonic complex vibrations as sums of diatomic vibrations called normal modes, right? We always bootstrap our complexity. We're in exactly the same process here. But we're just going to work up higher up the ladder, if you will. And our bootstrapping is we're going to take our atoms that we've constructed and put them together to make molecules by adding atoms things together, literally adding orbitals together. This method that we're going to talk about is what's called, there's lots of different ways to do this. This is kind of traditionally the classic way that it was developed. People talk about molecules and construct molecules in lots of different ways now. There's all sorts of different philosophical discussions about what a chemical bond is, how are they constructed from atoms. There's different methods that allow us to kind of work on those different frameworks. Because again, quantum mechanics is interpretive, right? It's about building a theory that explains experimental things. right? Through observables. You can, there's an interpretive question there. Or philosophy nerd, there's this idea of ontology. What's epistemiology? What is epistemically true? Well, so that's entirely dependent on the on your ontological observations of it. There's different ways to approach it. So we're going to do it kind of in kind of an old style way. It turns out to be kind of somewhat not the most useful for expanding to the most cutting edge, but I think conceptually it makes a lot of sense. And this method is called linear combination of atomic orbitals theory, right? Or we pronounce it LCAO. LCAO. This was invented a long, long time ago. When we first started thinking about molecules and starting how to build molecules from atoms, you know, the Bohr atom of hydrogen, how do we make H2 from 2 hydrogen atoms? This is the way that the physical chemists first started thinking of it. Let's just add the hydrogens together. Okay, so let's again do our due diligence and look at this from the point of view of a problem. Right? And of course, with atoms, we started with hydrogen, so it seems natural that we start with H2, right? Because we understand hydrogen very well. So let's put 2 hydrogens together. And let's see how this, what happens when we combine 2 hydrogens in their 1s state together. See if we form a bond, learn something about that bond. Right. So we're going to start from an initial state of 2 hydrogen atoms in their 1s1 or 2s0 configuration. All right, we're going to use a slightly more fancy language, right? They're doublet singlet. They're doublet s states. So we know what that orbital looks like. It looks like a sphere. All right, we should again think about, just like we did with the molecule or the atom, the helium atom, we should draw a little diagram of all the different moving parts. So we can look at our diagram for H2. Right. We're not going to think about nuclei as collections of protons. I mean, they're always just being collections of protons. We're just going to think about them as balls. So there's just hydrogen A and hydrogen B. We'll give the nuclei capital letters. So these are the nuclei. All right, we'll specify a distance between the nuclei, right? We should do that if we want to think about bonds. We'll call that big R. Those are our 2 nuclei. And it's just a proton. Right, and we've got, right, hydrogen is a 2-centered 2-electron system. It's got 2 nuclei and 2 electrons floating around it. Right, so this kind of looks like helium, but now there are 2 nuclei instead of 1. So there are, say, an electron over here, E2, an electron over here, E1. We can measure the distance between them, R12. We have vectors that connect the nucleus to the electron. So we'll call this like R1 sub A, right? So it's electron, that's the vector between electron 1 and nucleus A. There's a vector that connects B to 2, R2B. And of course, we also need to consider, right, we need to think about all the interactions. Electron 1 doesn't just interact with nucleus A and electron 2 just nucleus B. Remember, they exchange, they're indistinguishable. So E1 is also could be near B, and E2 could be on the other side as well. There's no preference. So we also have to consider those distances. Right, so there is a vector here pointing to 1 and B. And then, of course, there is the perpendicular one, R2B. So we've got lots of coordinates now, right? We have to track 2 electrons independently, 2 protons independently, and then the connections between all of them because they all exert forces on each other. So the Hamiltonian for this, we're just going to write terms. We're not going to write them out or solve anything. I just want to get a sense of what this looks like. Right? Again, we have kinetic energy terms. So we have the kinetic energy of the first electron, which we can track in terms of the distance from nucleus A. We have the kinetic energy for electron 2, which we can track from B if we want. That would be R2B. These are our electron kinetic energies. Right. We have the kinetic energies of the nuclei. They're jiggling around a little bit. Right. Again, right. So these are our nuclei kinetic energies. All right. And then we have a bunch of potentials, right? We have lots of electrostatic potentials. We have the interactions between the nuclei and each of the nuclei and each of the electrons. So there's 4 terms, right? Because there's 2 different sets of pairs. So these are our nuclear electron attractions. We have the repulsion now between the 2 nuclei. So this is A and B, my bad. Repulsion. Right, because they're 2 protons, they repel each other. They want to stay away. And then, of course, we have the electron-electron repulsion energy, which is the thing that gave us so much problem in helium. And hasn't gone away either. Right. The reason why I show this to you, the reason why I write this down is just to drive home the point that this is a completely coupled problem. Everything is connected to everything. Everything depends on everything. In some sense, there's almost no separability. How the hell do I separate things into individual coordinates? Everything depends on everything. Right? Nuclei depend on each other. The nuclear coordinates depend on the electrons. The electrons depend on each other. It's a messy system of many, many coordinates. In fact, there are 3 coordinates each. There's 12 dimensions of positions that I have to consider here, and they're all connected to each other. They're all 4 of these. But it's really, really hard for me to make progress here. Everything depends on everything. But this is usually I give a particular point right now that I actually gave you guys a long time ago when we started vibrations. We made an assumption in our vibrational problem about molecules vibrating about the motion of the nuclei relative to the electrons. We called it the Born-Oppenheimer approximation. And if you guys don't remember that name, that's okay. You'll certainly remember elephants with flies buzzing around. That's exactly what we have here. We have a system of nuclei, elephants, and 2 electrons, flies. And we know that they're all connected to each other, but we know that there are, in some sense, 2 different scales of motion. We have very, very slow nuclei that are very slow to move. They vibrate slowly. We know how they vibrate. And we have these electrons buzzing around it very, very rapidly. So in some sense, we know that there's some disconnect between the coordinates. The electrons buzz around the nuclei as if the nuclei are frozen. So we don't have to worry so much about the nuclei. The nuclei, of course, are moving because they vibrate. There's some nuclear kinetic energy, and there's some nuclear interactions, right? Of course, the electrons feel each other, and the nuclear components feel each other. Nuclei feel each other. They all feel each other, but in some sense, all the nuclear parts of it are moving so much more slowly than the electron part. So what we're going to do is separate this problem into nuclear component and an electron component, right? Just like we wanted to do in the Born-Oppenheimer process. Exactly the same process. And that's where we're going to make progress here. That's where we get our separability and how we even start to tackle this problem. It's that we can take advantage of freezing the nuclei and allowing the electrons to relax around. So let me just remind you what that looks like in practice. Right, so we're going to apply the Born-Oppenheimer approximation. Which is, of course, our elephant with our flies buzzing around over our nuclei. Right? And this is what we call the clamped nuclei approximation. Okay. So what we're going to do is we're going to fix the nuclear distance at some distance. Between the nuclei and allow the nuclei, or sorry, the electrons to relax around a static nuclear frame. All right, we got these nuclei freeze in some position. Okay, and remember what we did. We saw that when we looked at the energy of the molecule as a function of the position between the two nuclei. So this is the electronic energy. Let me write E-elect. This is the energy of the electrons. Right, we're going to move. Right, we're going to move the nuclei back and forth and freeze them. And in each position, ask the electrons, what's your optimal energy in arrangement? Right, the electrons are going to find the lowest energy state given the nuclear conditions. Right, that's what molecules and everything does in science or in physical science. Right, everything tries to find the lowest energy point. So we're going to move the nuclei and say, hey, electrons, figure out the best way to sit, and then read back my energy of those. Right, and remember, we get a curve that looks kind of like this, right? We call it the Morse potential. Right, we get the Morse potential. Right, and it says the Morse potential says that there's some point, right, R sub E, right, where the energy, the electronic energy is minimum. So the electronic energy reaches a global minimum. Well, we should say it's a local minimum. Say that, a local minimum at RAB equals RE, this equilibrium distance, right? So if we want to think about H2 in its most stable form, kind of the H2 that we see in real life, you know, at room temperature or just normal H2, we want to scan the distance between the hydrogens and relax the electrons and find the point of lowest electronic energy. And that is what we call the optimized geometry. It's the lowest energy structure of the molecule. It's the one that it shows in real life, right? It's the physical structure. So one of the goals in our system, or in chemistry in general, is to identify this point. We call this geometry optimization. Chemical structures physically exist only at local minima of the electronic energy. So the whole goal of finding a structure, if they were on a computer in one or two, I'm thinking like a theorist, that I know that that structure at the bottom of that, whatever I find in the energy structure, that's the best guess I have for what the actual structure looks like. And that's how we quantify whether our theory is good or not. Because then we go look at experiment, measure the bond length, and see if our calculations agree with our theory. But by and large, no matter what you do, I mean, there's no exceptions to this rule. Every structure you find, every chemical structure you find in the world exists at some minimum of energy. It's a general universal rule. Okay, so that's the whole point. This is what we're going to do. We're going to basically do the nuclear problem independently from the electron problem. We're going to move the nuclei, we're going to clamp them, and then jiggle our electrons and relax them, and then adjust our nuclei until we find the minimum energy and find this point. And I'll show you that example. I'll show you how the computer does this. Okay, so what does that do? That says what this leads to is that the wave function of our system, of our H2, is actually a product of two wave functions because we've separated the nuclear part. So there's a nuclear wave function, which we generally call chi, which is a function of the nuclear positions. And then there's an electronic part, which I'm just going to call phi. They're just labels. That's a function of the electrons. All right, so this is my nuclear wave function. And this is my electronic part. And of course, what that says is that the energy of H2 is equal to the nuclear energy plus the electronic energy. So the idea is that we can't separate the electrons apart. And by definition, we can't because they have to exchange. They're all the same, so they're all correlated. We can't clean this up anymore. But we can clean this up enough that we can move the nuclear part separately, calculate all of that at fixed position, and then relax this. Right? We fix this, and we calculate the wave function of the electrons that minimizes the electronic energy. Okay, which is just basically we move RAB and then we find this point, right? We move the electrons around and reach a minimum. All we're doing. Let's instead of we'll go and calculate this, and I'll show you how the computer does this. But let's just think about this from a basic point of view, because in the end, all we have now are two hydrogen atoms that we want to add together. Now let's see if we can make progress with just that simple addition. Right, and then maybe we can go back to the computer and ask it for some numbers. So let's think about things qualitatively first. So let's think about qualitative molecular orbitals, where we're just going to draw some things and see if we can make sense. We can make sense of what we think two 1s orbitals are going to do, and then we put them together at some distance. Okay, so what I'm going to do is I've got two hydrogen atoms at some distance from each other. All right, and I'm going to put them in a 1s state, right? So let's think a little bit about their wave functions. They're in 1s, right? So they're just spheres. Let me find my sphere drawer. Here we go. So here's HA and HB, and these are our 1s orbitals, so they're spherically symmetric. Right, so I've got a 1s1 orbital here and a 1s1 orbital here. Of course, they're in the 2s0 state, just to be precise. And what we're going to do is we're going to separate them at some distance. All right, we're going to fix them to some distance. call R. Okay, let's think about what this, let's lie on the bond, the internuclear axis, right? Let's sit on R and measure the probability of the electrons along R for the two atoms. Right, so let's think about what the electrons look like along this line. Right, so I've got this R here. Right, and I'm going to put the center of the nucleus of B, we'll call this B, and this A. And the center of nucleus A here. Right, I want to think about where the electrons are located in each of those atoms separately. Before I do any addition or anything, I just want to think about where they are. Right, so what I'm going to do is plot the probability of 1s1 on this. Right, and that is equal to the probability is equal to, remember, R squared times the wave function for the 1s, R squared. Okay, which looks like R squared e to the minus R, right? Roughly. Right, we're just getting rid of some constants. I don't care about normalization or, but roughly like R squared e to the minus R. Okay, so I'm writing R here as the distance of, say, electron A from A and the distance of electron B from B. So this is like R equals 0 for one, this is R equals 0 for another. So I'm going to do it relative to the center of the nuclei. And what R squared, right? This is the probability is going to grow as R squared and decay as e to the minus R. So electron A starts to grow in distance and then starts to decay away like this. So this is psi 1s A. And then B, the same exact thing happens, but it goes in the opposite direction. I have something that looks like this. Okay, so what I have are two, along R, I have two exponentially decaying distributions that in some sense somewhat overlap between each other. So we kind of have this region here, which I'll draw kind of like from here to here, in between the bonds where there seems to be some constructive overlap, right? You have some overlap here. Right, where they two overlap, right? So now what I'm going to do is add them together, right? We're going to do linear combinations of atomic orbitals. I'm going to say that H2 is a sum or a difference of these two hydrogens. I'm going to add the two wave functions together for the two atoms to create a new wave function, which is the sum of them, the combined atomic system. Right, so I can define our LCAO, or linear combination of atomic orbitals wave function, right, which looks like psi of H2 which is 1 over the square root of 2 times psi of 1s of A centered at RA plus or minus psi of 1s centered at B. Right? So that's just my linear combination of the two, right? I have two functions, two wave functions. Now I'm representing now as a combined set of two atoms being added together. And so my molecular wave function is just either a sum or a difference of the two. Okay, so what does psi squared look like? What happens now when I take this and I square it? What would the resultant wave function look like? So we have two different wave functions that come out of it. We have the plus combination. So I'm going to take R squared plus squared. That's this plus combination. And I'm going to take R squared times the minus combination. right? And the plus combination is going to be most intense where the two wave functions overlap the most, right? Because here I have these two adding together, but over here and over here, they're mostly independent of each other. So the middle is going to grow. The probability in the center is going to grow because they add coherent, like waves. All right, so what I would expect now for my radial part of my wave function is something that kind of grows up like this and then decays and then grows up again, decays like this. Right? And what I have now in this middle region is a growth of probability between the bonds, or between atoms. Right now, the electrons are being shared in the middle in this combination. Remember, I also created the negative combination. The negative combination is going to be depleted where they overlap. So another wave function, another state is constructed. Right? Where psi A minus psi B, I'm going to flip the sign of psi B, so they're going to cancel each other out in the middle. And so what I should expect is something that is strong on the outside. Because, of course, the electrons can be on the other side, too. And something that decays down the center. Sorry, let me do it like this. It decays down in the center. Right? In some sense, the electrons are pushed off to the side, right? Here, the electrons are coming together. And here, the electrons are being pushed away. Right? So we have two combinations. Right? So when we construct this system, this molecular system, we put in two atomic orbitals, and we get two molecular orbitals. Orbitals that now represent some sort of bonding. Right? This is a bonding interaction, right? All a bond is a sharing of electrons between two atoms. And that's exactly what we've created here. Right? We increase the probability that the electrons will be found in the middle just by adding the two, and they constructively overlap. So we give these names. This is called a bonding orbital. And this is called an antibonding. So in this system, we get bonding and an antibonding. Now, we know each two exist in real life. It has a single bond. So we know that this antibonding orbital doesn't seem to probably doesn't contribute to the ground state of hydrogen because we know it has a bond. Because this is why it's called antibonding. It's literally pushing electrons away from the center. It's the opposite of bonding. So I wouldn't really call it. I guess you could call it a repulsive state, but I don't really like to think of it that way. They're all repulsive states. Electrons are always repulsive. Just net attractive. It's just more that it just is separated. They're pushed away instead. They're just sequestered away instead. It's an insular bond. Right? So that's interesting. So the question, of course, is we don't have any sense from this about the energy. We know that we create bonding and antibonding orbitals, and they look different. So when we measure the Hamiltonian on them, when we measure the Hamiltonian on these wave functions, we should get different answers because they look different. These should be at two different energies. See if we can get a sense of what that may look like energetically. I'm going to now reformulate this problem in the language of our first problem set. We're going to find that the first problem set, by using vectors and matrices, will help us understand what's going on here and give us a sense of how these things change in energy. We should have some difference in energy. Remember, we started from a system, we have two identical atoms. The energy of this orbital and the energy of this orbital are exactly the same. Exactly the same atom. They're just different positions. And here what we've done is we've added two identical orbitals together to form two non-identical orbitals, the molecular orbitals. And so these two have the same energy, but these do not, at least our hypothesis. So let's see if the math works for that. All right, so let's use a little vector matrix and vector heuristic. This is a really simple problem. It's really not that much more complicated than our spin up and spin down problem, because our basis set, thing that we're constructing our wave functions from, are just hydrogen A and hydrogen B. There's just two components of our basis, just like there was for spin up and spin down. So what I can do is I can let my LCAO wave function for H2 be equal to a vector C1, we'll call it CA and CB, which is equal to CA times the wave function 1s1 located at A plus CB wave function located at atom B that represents a 1s1 hydrogen. All right, so what I'm just going to do is I'm going to represent my wave function as a superposition of atom A and atom B's atomic orbitals. Okay, so instead of thinking spin up and spin down, just think atom A and atom B. Okay, what do we know about this? Well, we can evaluate this, and we can think about how it acts on the base states. So if we interact H on 1, that gives me the energy of atom A. If I just have atom A, Hamiltonian is going to give me back the energy of atom A, which is just the energy of the 1s state, which we know is minus 13.6 eV. Right? And likewise, H on 0, 1 gives me exactly the same thing, right? Because they're the same atoms. Okay. But we also may have mixed states, right? I just showed you two mixed states. We have the superposition. We have, this is the 1, 1 state, and this is the 1 minus 1 state. On here. In that basis set, right? The superpositions. So we should, the Hamiltonian, right, should be a 2 by 2 matrix, just like the spin vector matrix was for the spin up and spin down. So the Hamiltonian's a 2 by 2 vector matrix. Okay. And remember, the diagonal elements give you the results for each of the base states. So this entry right here is going to be the energy of atom A. This is going to be the energy of atom B, bottom right. All right. So that's our energies of our base state. Those are just minus 13.6. And what I want to do, right? What I want to do now is I want to consider the fact that the two states are going to mix. Now, when I add them together, the actual observations, the actual states that I have are actually mixes of both. So I start from an initial condition where I have two atoms, and I'm going to add them together to get new states that aren't 1, 0 or 0, 1, but are some other vector on the circle, some combination of them. And the only way to do that is to add, remember, if we remember in problem set 1, when we defined spin up and spin down along the z-axis, that was a diagonal matrix, spin z, but spin x was an off-diagonal matrix. And what we saw was when spin x is applied to an up state, it converts it into a down state, up plus down. And if you put a down electron into it, it converts it into an up minus down state. So there's some and those were off-diagonal. So the off-diagonal elements are the mixing coefficients. They tell you how the two states mix together when you add them. And we know that they mix because we make these orbitals. These are the mixed states. I don't know how much they mix, but they mix by some amount. So I'm just going to put a number here called beta, which we'll call a mixing coefficient. Okay. Let's think a little bit about what the value of this is. So remember that these are columns and rows, that this is the column for psi A, this is the column for psi B, the row for psi A, row for psi B, complex conjugate. And so B is proportional to some product of A and B. Remember, Hamiltonian meant to integrate when we go from matrices to functions of X. So beta is going to be some value corresponding to the integral of psi B times psi A. So we can look at that. We can look at H11, which is this first one, which is EA. Well, this is the integral of psi A star H psi B star, or psi B, dx, or dr, which is also equal to H22, or sorry, psi A, and then H22 is equal to psi B, H psi B, dr. Right, and those are just equal to is equal to minus 13.6. Right? So the diagonal elements are just minus 13. And so from this construction, we can see that the diagonal elements just take the wave functions from that row and vector and put them in this interval. So the off diagonals is going to bring one unit of A and one unit of B. So H12 is equal to beta, and that's going to be the integral of psi B star times H psi A dx. H applied to psi A gives me minus 13.6 EV. I can factor that out, and I get psi B star psi A dr. And all that I have left here is the overlap between B and A. This just tells me how much B and A overlap with each other. If they're completely separate and orthogonal, this is 0. But we just drew it that they're not. They overlap. Right? This overlap here that I've drawn here is the value of that integral. It's the overlap between the product of A and B, which is where the product is tense, and that's in the middle. So this off-diagonal element is just the overlap of the two atoms. All right, so if the two atoms appreciably overlap, at least theoretically, if they overlap geometrically, meaning that they both have probability in the same space, we're going to mix two atoms together because B is not equal to 0. That's going to mix. That's going to create two states that are a sum of atom A and B, the difference of atom A and atom. Right, so let's see what happens. Right, I know that if our atoms appreciably overlap, they're in the same space if probability that's shared. I have a non-diagonal matrix. So in an overlapping system, I have that the Hamiltonian is equal to E1s beta E1s. Right? Remember that this is in the basis of 1, 0 and 0, 1. I know I can convert this into a basis of combined orbitals. I can convert this now. Right? I can change my basis to some coefficients CA and CB such that I can rewrite the Hamiltonian in this basis where I am completely diagonal. Right? And the basis for this is CACB, which is CA times 1, 0, plus CB times 0, 1, where CA squared plus CB squared is equal to 1. Right? Where and if B is not 0, then CA is not equal to CB, which is not equal to 0. So there's some mixing. The atoms mix. And what do they mix into? Well, we have two new wave functions for our system. We have the plus combination, which is Ca psi A, 1s1, plus Cb psi B, 1s1. And then we have the negative combination of them, which is that Ca psi 1a, psi s1, minus Cb psi 1s1. And these are our bonding and anti-bonding orbitals. So when the two atoms mix, they automatically form two new orbitals that are combinations of the two atoms. One of them is bonding and one is anti. The energies now are different. Because now up in this basis, I have two identical states. 1, 0, and 0, 1. They're exactly the same atoms, exactly the same state, same energy, right? They're degenerate. And here what I've done now is I've let them two interact. I form a new set of states, which are superpositions of the atoms. And they're different. One's a plus and one's a minus. They're different states, therefore they have to have different energies. So E plus and E minus can't be the same. Okay, so I form when my two atoms come together, starting from two orbitals that are exactly the same, and they split into an orbital that has a different energy than the other, which means that one has to go down. Well, hopefully, one has to go down, and the other one has to go up. That's the way. So let's draw a diagram of that. By the way, just a heads up. These are what we actually call molecular orbitals. Right? They are orbitals that represent the interactions of two atoms in a bond constructed from two atomic orbitals. LCAO, linear combination of atomic orbitals. Okay, so let's look at diagram. What would this look like on an energy diagram? Well, I could start with, we start at minus 13.6. Let me make a little more space here. So let's draw an energy diagram. We start at minus 13.6. We have atom A here. And then over here, I'm going to draw atom B. These are 1s1 orbitals. Right? They're at the same energy. They each have an electron. We want to pair them, of course, so I'm just going to flip them. I have two identical atoms. Right? And then I'm going to combine them together into two orbitals that have different energies. Right? We're going to combine them symmetrically. A and B are the same. So one of the orbitals is going to go up by the same amount the other one goes down. So I'm going to create a new orbital, a molecular orbital, that's at lower energy, our bonding combination, and one at slightly higher energy, which is our anti-bonding combination. And the splitting here is equal to 2 beta. So the more the two atoms overlap, the more the molecular orbitals change in type, and then they change in energy. Okay, so what happens now? Well, we combine them, and of course, electrons, because of Hund's rules, electrons are all going to go into the lowest energy state. So we form a bonding orbital with 2 electrons in it, and an antibonding orbital with no electrons in it. Right? This is a 1s2 state, right? Because we have 2 electrons. Well, it's a 1s1 plus 1s2, so we call that a 1s2. That we've now constructed from HA and HB. Okay. So what we've done now, by filling them now, we now have a molecule that has a fully filled, completely paired off bonding orbital. We have a bond. It's a bond. In general, we can define something called the bond order, which I introduced on the homework last time when I shouldn't have, which is the number of bonding electrons minus the number of antibonding electrons divided by 2. And so for H2 in the 1s2 state, this is 1/2 2 minus 0, which is 1. And we call this, of course, a single bond. So this is a covalent bond. This is by definition a covalent bond. We have 2 electrons coming together into a single orbital that are perfectly equally shared between them. This is the definition of a covalent bond. What do these orbitals look like? Well, let's go back to our picture. Remember, I drew these along R. Okay? But remember, there's also there's 2 angular, right? So we're just looking along one of 3 dimensions, the R dimension. But remember, in the s orbitals, the angular part doesn't matter. It's a sphere. So this function is actually spherically or cylindrically symmetric. Cylindrically symmetric. If I rotate any angle out of the plane around the bond, I see exactly the same thing. Right? So this is a cylindrically symmetric system. It maintains the symmetry of the s orbitals. So it's the same in all angles. So what do these look like? Well, we first have one that looks 2 spherically symmetric potentials or orbitals. These are spherically symmetric. And we're going to get something that's cylindrically symmetric. We're taking 2 spheres and kind of stretching them and sharing them together. That forms a cylinder. And so I'll put my 2 atoms A and B here. Right? It gets kind of thin at the edges. And it gets kind of fat. Like that. Right? And it's cylindrically symmetrical. I'm not drawing it very well. Take some pictures that we'll look at them on the computer tomorrow, our next class. Right? So we have this cylindrically symmetric orbital. We give this a name. This is what we call sigma symmetry. So this is what's called a sigma orbital. And sigma just means S-like. In molecules, we promote the Roman letters, Latin letters, Greek letters. So sigma is S. So things that look S-like, so symmetric things, or spherically symmetric things, what we call sigma. We'll see later when we combine P's together, we'll form orbitals called pi orbitals, which have the symmetry of the P orbitals, but they're molecular, called them pi. For the D orbitals, they're called delta orbitals, and so on. So there's this addition. And then we also have the antibonding combination. Right, but we do a minus here. instead. And of course, what that really means is that we're actually summing a positive wave function. This is a positive wave function plus a negative wave function. I think that's a better way to look at this. This is a negative function. Well, they're just opposite signs, and we're adding them together. And so that's going to cancel out in the middle. It's also going to be cylindrically symmetric. That's a really bad picture. We typically draw them a bit like this. Something like this, two balls. And then there's a node right in the middle. There's no electrons. And we call this an antibonding orbital or sigma star, right, where the electrons are repulsive. So this is the sigma star orbital, and this is the sigma orbital. How much time do I got? Great. Let's go. We should try to figure out a little bit about how big beta is for H. That's probably good, right? We've identified that they should form these new orbitals, but the question is how much do they really change? How much do the energy change? All right, so how are we going to do this analysis? So let's figure out how to experimentally determine the energies. All right, well, we can use electron ionizations, right? Because we have a nice reference that we know exactly. That ionizing electrons has an energy of 13.6 electron volts. Okay, so in our diagram, we can put a zero energy because we put it negative. This is where the electrons ionize. This is the ionization limit. Right, so we know that if we take an electron from here, it's 13.6 eV. We take an electron from here, it's the same. So the question is that in H2, well, let's do the same thing. We have two electrons here. How much energy does it take to ionize H2? And the difference of those two values is going to be the stabilization, right? It's the difference between the 1s states and the hydrogen sigma orbital. Right, so the way we're going to do this is the technique that we're going to use. It's called photoelectron spectroscopy. Right, where we're going to use a laser of fixed energy to ionize our system and measure the orbitals by how much energy is left over. So let me give you an example. So let's say we ionize this H2 or H with a laser. All right, and we'll do it at 16 eV. Right, this is in the what we call the ultra. This is in the high ultraviolet, extreme ultraviolet. There's only a few places in the world that can generate this kind of light, but you can do it. Actually, you can do it on a tabletop now. Right, you're going to tune laser at 16 eV. We're going to ionize H and H2. Okay. So we're going to take H and we're going to add 16.0 eV. And we're going to get H plus. And we're going to get an electron that's flying off somewhere. Right? And the energy of the electron, so delta E, the binding energy, is going to be the energy of the laser minus the kinetic energy of the electron. We're going to see that electron fly off somewhere. Right? It's going to detach, and it's going to fly off with some energy. And the binding energy of the electron is whatever's left, right? We're going to feed in 16, and let's say it flies off with 2 eV worth of energy. That means that the binding is 14. Because it took 14 eV to remove it. Okay, so we know that H plus plus E is 13.6 eV. We know that exactly. And now we do H2 to H2 plus E. Let's go look it up. The first, I'll just let Gemini, this is the correct answer. The first ionization of H2 is 15.4 eV. Okay. So what's the difference, right? Well, the difference now is, so this is 15.4. And so the gap between the bonding orbital, the stabilization energy is just the difference of those two numbers. We want to calculate that. That's beta. And so beta is equal to 15.4 minus 13.6 eV, which is 1.8 eV. Right? So what this is saying is that hydrogen, H2, stabilizes the two H atoms by approximately twice this, because there's 2 electrons in that orbital. (3.6 eV). That's bonding, right? That's where the stabilization of bonds come from. Why bonds are stronger than atoms and more stable than atoms is because when you add 2 an electron or 2 atomic orbitals together, it creates a combination that is lower energy than the initial state. And so naturally, everything's going to fall into it. That's why at low temperature, all H is H2, because that 3.6 eV is like 300 and 400 kilojoules per mole. That extra 300, 400 kilojoules per mole you get there is what drives molecular formation all the way, why we don't just exist in a world of atoms. Right? And that just comes for free. Right? It just comes from the natural stabilization of 2 orbitals coming together to mix, creating a state that is now more probability, more in some sense, less oscillating, lower frequency, because there's more positive amplitude now, less frequency, and therefore lower energy. There's less nodes, right? There's more probability, everything's shared, the energy will be lower. That's how we form bonds, right? Bonds just naturally come out of the interaction of atoms and their wave functions. Okay. So let me show you I'm going to show you some pictures. Now, of course, what I can also do, we should also consider excited states, right? I could put these electrons in different orbitals. I could take one of those electrons and put it in the antibonding orbital. I could even put both of the electrons in the antibonding orbital, which, by the way, does not take nearly as much energy, right? It takes 15 eV to remove the first electron, and then probably another 15 eV to remove the other one. I think it's 16 or 17. So it takes roughly 30 some eV to remove both the electrons and hydrogen, but it only takes 3.6 times 2 for me to take the H2 electrons and put them in the antibody orbital. It's a less distance to go to the end. So there are other types of excitations that I can do. And so I kind of want to show you a picture of this, just to kind of give you a sense of what it looks like. Just a second, I'm going to copy it over. I'm going to erase some junk here. This is from an old lecture. This is experimental data of the different electronic states of H2. So each of these curves that you see here are different arrangements of the electrons in the molecular orbitals. And I'll try my best to describe them. Right, so this is in a weird unit called AU. This is an atomic unit. Hartrees we talked about it before. One Hartree is roughly two hydrogen 1s electrons, right? So you can see that we should expect two hydrogens to be around right here, atoms by themselves. We can see H2 is slightly lower than that because, again, it forms a bond. It's more stable than two hydrogen atoms. This is the hydrogen limit. And you can see that it's the hydrogen limit because as you stretch these bonds, you see that it goes to about 1.10, right? So this is 2 times the energy of a hydrogen atom. Right? You can see it's about minus. Right, so this bottom state right here is the Morse potential for H2 in a ground state. You can see it's nice and deep. Right? This is the 1s2 state. It's nice and deep. Right? And you can see that as it starts to go out, what does it dissociate to? Well, it dissociates into some state that looks like 2 hydrogen atoms in the 1s state. So the dissociation limit here is H1s1 plus H1s1. Right? So what I know is that if I take H2 and I stretch it, H2 in the ground state and I stretch it, I end up with 2 hydrogens in their ground state. Okay, it undoes itself. Now let's imagine I excite one of the electrons from the bonding orbital to the antibonding orbital. Right, so this state is this. But when I excite one of the electrons, now I have a discrepancy. I can put it down like this, or I can put it up like this. It could be a triplet or a singlet. Well, you can see that there are the next 2 limits right here is this one and this one. This one is low in its bonding. It's slightly less. It's a weaker bond. There's also a level of 1s sigma. This is the singlet of where I take this electron and put it up here unpaired. So you still have, you in some sense have half a bond. So this one right here is this state. Let me make that a little bigger. Right? You have an excited hydrogen atom or molecule. It's still bonded, but it's just not as strong as it was before because now you have one of the electrons on the orbital. Now look what happens. So the next one is a triplet. This means triplet, which means that I have the spins in the same state. Right? This one would be this combination. And notice it doesn't have a well at all. In fact, it just looks like a slope, right? So if I put any system, like imagine I start with a molecule here at the bottom, normal H2, and I use a laser to excite it here. What does the system do? Well, this is a potential energy. The system always wants to go to potential energy, the lowest potential energy. So if I'm in this state, I fall to this well right here, right? This is the lowest energy point. It's a nice stable bond. In this state, it just goes down the hill all the way out. This is a repulsive state. This is no bond. So there is no bond for this. Right? Because the state is repulsive. It just drives, atoms go down this hill. So 1s1 plus 1s1. So this is repulsive. Right? This is why spin is important, right? We have 2 states that are in some sense have the same configuration in terms of where the electrons are, but one has spin flipped and one spin paired, and that turns the bond on and off. the repulsion of the two light spins is so significant that it just turns the bond off. There's no more bonding interaction. Completely repulsive. It's dominated by the repulsion of the two light spin electrons. Notice what happens now. Eventually, though, I can excite to the next orbital, right? Because what am I going to have? Eventually, I'm going to have the two s orbitals come together. And then I'm going to have the three s orbitals come together and the four s orbitals come together. And there's the bonding interactions for all of these. Right? So this is, for instance, this state. Is the 1s sigma. There's going to be a 2s sigma when we add the two s's together. 2s sigma star. And this state right here, the first one, is this state. And then the next one is the 3, and the next one is the 4. Right, so this is 1s, and this is 4s sigma. And so on and so forth. So there are lots of different ways to make bonds in hydrogen, but not all configurations of all electrons are stable. And as you can see, when I put an electron in the 2s, 3s, and 4s, those bonds are much less stable. The wells are much smaller. They're just very weak, floppy bonds. And because they have very, very little depth, right? Very weak wells. So they only bond very slightly, but they're not repulsive. You may notice, for instance, that there is a cusp here. Kind of odd too. That turns out that that's actually another state that's hiding behind. That's hiding, that you can't see. There is another state that you can't see that is repulsive, which is the triplet 2s. So this state that's hidden here in this 1s sigma, and then the same pair in the 2s, but spin, with the same spin. This is a repulsive state, and they meet at the same point right here. There's two energy levels that at a given position, they're exactly the same energy. So there's two states that meet there. You can see they then disassociate to the same amount, and what they disassociate to is hydrogen, one in the 1s one, and the other one in the 2s one. Okay. So it depends on what state you're in, what products you get. And it also depends on what state your hydrogen atoms are in, depending on how strong the hydrogen bond between the two hydrogens. And as one electron gets more and more excited, the bond gets weaker. We'll look at that more carefully as we proceed. Okay. One more picture. This one doesn't require any drawing. I just want to show you what the molecular orbitals look like. These are three-dimensional pictures of each orbital. We'll recalculate these in the class. So here's the 1s sigma orbital. You can see again, it just looks like a giant sphere surrounding. The electrons can be anywhere. This person shared. The sigma star orbital, separate different phases. The electrons are pushed away from each other. This is the 2s sigma. You can see that they're bonded together. It's a little more close. They're not as bonded as well, so the overlap is weaker. So the orbital is smaller. But the 2s sigma, they love to push away. It's got a big sigma orbital. And these ones here, you can start to see that now we're starting to get slightly different behavior. This looks like an ellipse, but this one kind of looks like a hot dog one. These are orbitals that connect the p. These are pieces. So these are the two p orbitals combined together. So every orbital in hydrogen adds to every other orbital in hydrogen, and you can put electrons into any of them. If provided enough, you have enough energy, though you're not guaranteed that when you put an electron in, that the molecule continues to exist. Like completely dependent on the state. But we're going to see these kinds of patterns in molecular orbitals and designs, not just in H2, but all sorts of different molecules. Very common. So what we'll do next class is we'll make things a little more interesting. For the next lecture, we'll look at molecules with electronegativity. Right? We'll look at HCl, O2, things that are other than hydrogen. How do we find p orbitals? And then on the final lecture, I'll talk to you about hybridization, talk about sp3 orbitals, and we'll talk about why carbon has to be tetrahedral. And I'm going to prove it to you that methane is tetrahedral. And I'll explain to you why the tetrahedral arrangement is the only one that's possible. That'll be our final lecture. All right, you guys have a good one.
Since